In this class, we will explore some more examples of groups. Now, we have already seen in the last class that Z with respect to addition, set of rationals with respect to addition, set of reals with respect to addition, and set of complex numbers with respect to addition. These are the examples of groups. Now, let us try to check whether the same sets are groups with respect to subtraction or not. Remember, I have already given few examples in the lecture of binary operation. We have noticed that the subtraction is actually not associative, right? Thus, all these sets Z, Q, R and C will not be groups with respect to subtraction. The property that is failing is associativity. Now, natural operation that we are going to think of is multiplication. Now, we have to check whether all these sets are groups with respect to multiplication or not. Talking about the first set, let us say Z. Remember, group says the set should be non-empty. Z is non-empty together with binary operation star. So, multiplication should be a binary operation on Z. It is, right? If you take two integers, the multiplication of two integers is again going to be an integer. So, that is not an issue. Now, one by one we will check the properties. Now, talking about associative property. So, if you take three elements of Z and if you try to find A multiplied by B multiplied by C, and you will see that this is actually A, B, C. Also, A multiplied by B multiplied by C is equal to A, B and C. I mean, if we have two numbers 2, 3 and 5. So, if you multiply 2 and 3 first, and if you multiply 3 and 5 first, so answer will not change, right? Let us do it then. So, 2 multiplied by 3 is actually 6 multiplied by 5 and 6 5s are 30. Now, if you multiply it by 3 and 5 first, then it will be 2 15s are and that is also 13. So, this we have checked for 3 elements in particular, but this is satisfied for all the elements of Z. So, no issues there. Multiplication is associative in Z as well. Now, talking about the identity element. Now, remember, what does the property say? There should exist E belongs to G such that A star E should be A. But our star is multiplication, our J is Z. So, we have to find that exists means what? To find E belongs to Z such that A into E should be equal to A, which is equal to E into A for all A belongs to Z. So, can you guess such an element of E, such an element E belongs to Z where A multiplied by E is actually equal to A? A particular case. So, if we have 5, so 5 multiplied by what is actually equal to 5? That is 1, right? Isn't it? Yeah. So, the same element will work here. So, A multiplied by 1 is actually equal to A, which is further equal to 1 multiplied by A. So, identity exists in Z with respect to multiplication. Remember, the identity with respect to addition was 0, the identity with respect to multiplication is 1. So, we will say there exists 1 belongs to Z such that A into 1 is A, which is equal to 1 into A for all A belongs to Z. So, that has also happened, right? Now, the question is existence of inverse. Now, talking about existence of inverse, what does the property say? For each A belongs to Z, there should exist, we should be able to find A inverse belongs to Z such that A multiplied by A inverse. Now what is our identity element? 1 should be equal to 1, that should be equal to A inverse into A. A particular example, suppose we have 5. So 5 multiplied by what is equal to 1, that is further equal to that element multiplied by 5 pi. So can you spot an element here for which this condition is satisfied? Yeah, that is nothing but 1 upon 5. But the question is, does 1 upon 5 lie in Z? Because what is the property saying? For each A belongs to Z, there should exist A inverse belongs to Z again. So the issue lies here. This phi inverse in this case is 1 upon 5, but this 1 upon 5 does not belongs to Z, and that is the issue, and therefore Z is not a group with respect to multiplication. But does it apply for set of rational numbers as well? I don't think so, because 5 is a rational number. So 5 inverse again will be 1 upon 5 for set of rational numbers with respect to multiplication, right? So in that case 5 inverse exists. Does it applies for every rational number? That is a question. For example, if I take 2 upon 3, so 2 upon 3 multiplied by what is equal to 1, that is what we are checking, right? And your answer will be 3 upon 2, right? Because 2 upon 3 multiplied by 3 upon 2 is equal to 1. So it seems that the inverse of 2 upon 3 also exists in set of rational numbers. So the question is, will inverse of each element in set of rationals exist? Remember, that is one special element in set of rationals, which is nothing but, yeah, how you have to think? What actually we are doing in order to find inverse? If we have 2 upon 3, we are getting 3 upon 2. We are taking reciprocal, right? So 0 is there in Q. If you take the reciprocal of 0, what is that? 1 upon 0, but that quantity does not exist, right? That is the issue for set of rationals. Same issue is for set of reals and set of complex numbers. Thus, our conclusion is Z, Q, R and C are not groups with respect to multiplication. The reason is the multiplicative inverse of 0 does not exist in all these sets.